Our planet, this beautiful blue marble spinning in space, has a story to tell. It is a story not of months or years, but of millions and billions of years. This is the story of Earth's climate. It is a tale of incredible change, fire, ice. The world we know today is just one page in a very, very long book. To understand our present and to look towards our future, we must turn back the pages. We must listen to what the Earth itself is telling us. This history is written in the rocks beneath our feet, in the ice at the poles, and in the fossils of long-lost creatures. It reveals a world that has been in constant motion, a world of dramatic transformations. For most of its existence, Earth has been a very different place. Sometimes it was much, much hotter than it is today, with no ice at the poles at all. At other times it was so cold that vast sheets of ice covered almost the entire globe, a true snowball in space. Let us travel back in time, far beyond any human memory. We go back not thousands, but billions of years. In its infancy, around 4.5 billion years ago, Earth was a hostile and fiery world. Volcanoes erupted everywhere, spewing gases into the sky. This formed the planet's very first atmosphere. It was not an atmosphere we could breathe. Carbon dioxide, nitrogen, water vapor, but it held no free oxygen. This thick blanket of gases trapped heat from the young sun, creating an intense greenhouse effect. The surface of our planet was a molten, bubbling landscape, a truly inhospitable place for life as we know it. Over hundreds of millions of years, the planet began to cool. The water vapor in the atmosphere condensed and fell as rain. This rain fell for centuries, creating the first oceans. It was in these ancient oceans that the first simple forms of life appeared. Cyanobacteria, photosynthesis, oxygen release. This was a turning point in our planet's history. For the first time, oxygen began to build up in the atmosphere, slowly, steadily, over an immense stretch of time. The rise of oxygen had a dramatic effect on the climate. It reacted with methane and removed it from the atmosphere. This caused the planet to cool down significantly. This event, known as the Great Oxidation Event, changed the world forever. It paved the way for more complex life forms that could use oxygen to breathe. But it also triggered a climate crisis of its own. Imagine a world almost entirely covered in ice. Not just at the poles, but everywhere. A white, frozen sphere with ice sheets possibly a kilometer thick, stretching all the way to the equator. This is not science fiction. Scientists believe this happened at least twice in Earth's deep past, around 700 million years ago. They call this period Snowball Earth. The evidence for this extraordinary event is found in ancient rocks. Geologists have discovered deposits left behind by glaciers in places that, at the time, were located in the tropics. It is a startling thought. A world where even the warmest parts of the planet were frozen solid. It likely began with the arrangement of the continents. Most of the land was gathered near the equator. This led to increased rainfall, which washed carbon dioxide out of the atmosphere and into the ocean. With less of this greenhouse gas to trap heat, the planet began to cool. As ice sheets formed at the poles, they reflected more sunlight back into space. This made the planet even colder, causing the ice to spread further. This feedback loop, where cooling causes more cooling, eventually ran out of control, encasing the planet in a shell of ice. Life, however, clung on. In the deep oceans, near volcanic vents, or perhaps in small patches of open water, simple organisms survived. Volcanoes continued to erupt, pumping carbon dioxide back into the atmosphere. With the surface frozen, there was no rain to wash this gas away. Over millions of years, CO2 grew to incredibly high levels, creating a supercharged greenhouse effect. Eventually, ice began to melt at the equator. As dark ocean absorbed more sunlight, warming fed on itself. The thaw was likely rapid. The planet swung from an extreme ice age into an intense hothouse, reminding us that Earth's climate system has tipping points. After the great freezes and thaws, the planet entered a long period of warmth. After the great freezes and thaws, the planet entered a long period of warmth. This was the Mesozoic era, best known as the Age of Dinosaurs. for more than 150 million years. Triassic, Jurassic, Cretaceous. Earth was a greenhouse world. Global average temperatures were much higher than they are today. There were no permanent ice caps at the North Pole. There were no permanent ice caps at the South Pole. The world was a warm, humid place, a paradise for reptiles. Dinosaurs, large and small, roamed every continent, from the equator all the way to the polar regions, which were covered in lush forests instead of ice. The evidence for this warm world is abundant. Fossils of warmth-loving plants like ferns and cycads have been found in places that are now frigid, such as Alaska and Antarctica. The remains of crocodiles and turtles, which cannot survive in freezing conditions, have also been discovered far to the north and south. Tiny fossil shells show that the deep oceans were significantly warmer than they are today. This long period of heat was sustained by high levels of carbon dioxide, largely from intense volcanic activity as Pangaea broke apart. Around 66 million years ago, a massive asteroid struck. The impact was catastrophic, lofting dust that blocked out the sun and plunged the world into a sudden deep cold. Plants died, the food chain collapsed, and about 75% of species vanished, including all the non-avian dinosaurs. The event demonstrates the planet's vulnerability. It opened the door for the rise of mammals, and eventually, us. How do we know so much about a past that no human has ever seen? Well, we know it because the Earth keeps a detailed diary. We just need to learn how to read it. Scientists drill deep into the ice and pull out cores with distinct layers trapping tiny air bubbles. Those bubbles let us directly measure greenhouse gases, carbon dioxide and methane. The ice also holds temperature clues in the isotopes of water, revealing the temperature when the snow fell. Together, they build a year-by-year and decade-by-decade record. For at least the last 800,000 years, CO2 and temperature have moved in lockstep. Another page is written in ocean sediments, dust, sand, and the tiny shells of foraminifera. By drilling cores, scientists analyze shells from different layers to reconstruct ocean temperatures over millions of years. This sediment record corroborates the ice, giving a broader global picture. Fossils also guide us. The types and shapes of ancient plants, even palm tree fossils in Wyoming, reveal warmer past climates. Jagged, smaller leaves indicate colder, drier periods. By piecing together ice, sediment, and fossils, scientists build a detailed, reliable history of Earth's changing climate. The answers are not found in opinions, but in the evidence. The clues are all around us, waiting to be read. Let us now begin our journey and explore the untold truth of our planet's remarkable climate past. After the warm era of the dinosaurs and the subsequent cooling, the Earth entered a new phase about 2.6 million years ago. This was the Pleistocene Epoch, more commonly known as the Great Ice Age. Not one single freeze, but long glacials punctuated by shorter, warmer interglacials. Massive ice sheets, kilometers thick, advanced from the poles, lowering global sea level by up to 120 meters. These rhythms were driven by subtle, predictable changes in Earth's orbit. Milankovitch cycles, a wobble in the axis, changes in tilt, and orbital shape. When the north gets less summer sunlight, snow doesn't melt and ice builds up year after year. Life adapted. Woolly mammoths, saber-toothed cats, and giant ground sloths thrived in cold, open grasslands. In interglacials, ice retreated, forests returned, and hippos and elephants spread northwards. Our species evolved and spread, shaped by these cycles, developing tools, clothing, and social structures. As orbital cooling began, CO2 fell. Colder oceans absorbed more, amplifying the cooling. Then, as warming resumed, CO2 was released, amplifying deglaciation. This feedback cycled CO2 between about 180 and 280 parts per million. The Ice Age heartbeat set the stage for the world we know. About 11,700 years ago, the last great glacial period ended. Ice retreated, seas rose, and Earth's climate entered a new phase. This is the period we are living in now. It is called the Holocene Epoch. Compared to the wild swings of the Pleistocene, the Holocene has been remarkably stable, within about 1 degree Celsius. This calm enabled agriculture, domestication of animals, and the first villages. Then towns, then great cities and empires. Everything we call civilization, writing, art, science, government, was built on predictable food supplies from a stable climate. Natural systems kept CO2 near 280 parts per million for millennia. There were minor fluctuations, the medieval warm period, when parts of the North Atlantic were slightly warmer, enabling Vikings in Greenland, followed by the Little Ice Age from the 14th to 19th centuries, with advancing glaciers and harsh winters in Europe. These were primarily regional shifts, not the dramatic global swings of the Pleistocene. The Holocene's balance fostered our flourishing, until, in the last 2 centuries, that long stability came to an abrupt, dramatic end. For thousands of years during the Holocene, atmospheric carbon dioxide held steady at around 280 parts per million. Then came the Industrial Revolution. Burning coal, then oil and gas, powered our world, while releasing vast stores of ancient carbon. By 1950, CO2 reached about 310 ppm. Today, it has soared past 420 ppm. Levels like this haven't been seen for at least 3 million years, and the rate of change is unprecedented. Natural deglaciations raised CO2 by 80 ppm over thousands of years. We've added over 140 in just 2 centuries. Isotopes identify fossil fuels as the source, distinct from volcanoes or oceans. Emissions data match the atmospheric rise. As physics predicts, more greenhouse gas traps more heat. The result, accelerating global warming. We see it around us. Melting glaciers, rising seas, shifting weather with more frequent and intense heat waves, droughts, and heavy rainfall. We've pushed Earth out of the stable Holocene state into a rapidly changing climate. The science is clear. The huge increase in atmospheric carbon dioxide is our doing. Over the last 800,000 years, CO2 cycled between about 180 ppm in ice ages and 280 ppm in interglacials. For all of human civilization, it stayed near that upper peak. Today's level above 420 ppm is far outside this natural range, a near vertical spike. Past warming out of the last ice age was about 5 degrees over 5 millennia. Current and projected warming is many times faster. Ecosystems had millennia to adapt. Today, they have mere decades. Yes, the planet has been warmer with higher CO2, but those changes unfolded over millions of years. Humans weren't around, continents were in different positions, and without ice caps, sea levels were tens of meters higher, conditions incompatible with our coastal civilization. History shows CO2 is Earth's main climate control knob. High CO2, warm planet; low CO2, cold planet. By raising CO2 to levels not seen in millions of years, we are turning that knob up, and the climate system will respond. The only questions are how much, how fast, and what the consequences will be for life on Earth. The Earth's climate story does not end today. We are living through one of its most dramatic chapters. What we do now will write the next page. Scientists use models grounded in physics and chemistry, tested by reproducing past climates, to project a range of futures. The future depends on how much we emit. If emissions stay high, models predict several degrees of warming by century's end. A few degrees globally is enormous. The difference between an ice age and a warm interglacial was only about 5 degrees. Profound changes follow. Extreme heat becomes common, agriculture and water supplies are disrupted, sea level keeps rising, ecosystems strain, extinctions spread. History shows feedback-driven runaways. Scientists worry about tipping points now. Thawing permafrost could release methane, amplifying warming. Greenland and Antarctic ice sheets could cross thresholds, locking in meters of sea level rise. Once crossed, some changes are irreversible on human timescales. Yet Earth's past also shows that change is possible. Life reshaped climate before. Today, humanity is the dominant force. We are the ones turning the dial. The facts, written in ice, stone, and the air itself, show our emissions are linked to warming. The future isn't written yet, but history gives a clear, urgent warning.